As we prepare to work with logarithms and exponents in Chapter 4 of College Algebra, let's review some of the laws of exponents that I know you have studied before but might need a refresher. Law number 1 tells us if we are multiplying terms that have the same base and different exponents, all we have to do is keep the same base and add the exponents. I realize sometimes in variable form it's a little confusing to see everything with variables, so let me show you a quick example. If we had x to the third and we wanted to multiply that times x to the fourth, according to this rule, we would end up with the same base, which is x, but we add the exponents, and 3 plus 4 is 7. Now, Law 2 gives us the rule for dividing when the bases are the same. That simply means we would subtract the exponents. Now, there's two different ways you can think about this. You can either subtract the smaller number from the larger, and that would mean the new exponent goes on that base in the location where the larger exponent was, or you can always subtract the bottom exponent from the top exponent and never have an answer that's a fraction, but you may end up with something that has a negative exponent. Let me just show you very briefly if we apply this law to something like x to the sixth divided by x to the second. If we subtract the smaller exponent from the larger, 6 minus 2 gives us 4. Because the 6 is the exponent on the top, it means we would have x to the fourth in the numerator, and we wouldn't have anything in the denominator except 1. So x to the sixth divided by x squared would give us x to the fourth. Now, Law 3 tells us if we have a product and the entire product is raised to a power, each individual factor of the product is also raised to that exponent. This is probably pretty straightforward as long as the products involved are variables. This would be an example of what I find students struggle with the most. Let's say we had a constant times a variable. Maybe we have 2x in parentheses, and the entire thing is being raised to the third power. Well, that means 2 gets raised to the third power, and x gets raised to the third power. Then they'll be simplified and put back together. 2 to the third means 2 times 2 times 2, which is 8, x to the third. So that would be a simplified example of Law 3. Law 4 tells us if we happen to have a fraction raised to a power, we can raise both the numerator to that power and the denominator. Let me give you a quick example of that. Let's say we had the fraction 2/3 and that entire fraction is being raised to the second power. That would mean that's the same as 2 to the second power over 3 to the second power. When we clean this up, it would give us 4 over 9, simplified form. Now notice that according to this law, we have to recognize that the denominator in our fraction cannot equal 0 because that would be undefined or a meaningless expression. So provided that denominator is not equal to 0, this law will look the way that we just used it. Now Law 5 tells us if we already have something raised to a power and then it's raised to another power, we simply multiply exponents. So for example, if I had x to the third and I wanted to raise that to the fourth power, that is the same thing as x to the 3 times 4, which is x to the 12th. So if it's a power raised to a power, multiply exponents, that's Law 5. But if we're multiplying and the bases are the same, look at Law 1, that means we add the exponent. So you'll have to be careful you keep those two laws straight. Law 6 is one that I hope you've already memorized, But if you don't understand why anything raised to the 0 power will equal 1, and that's assuming that the base is not 0, here would be a quick explanation of why this would work. Let's go back and look at what we saw in Law 2. Let's say we had x to the third divided by x to the third. So if I use Law 2, that tells me I can subtract the exponents. That would be the same as x to the 3 minus 3 power, which is x to the 0 power. But look at what we started with. We had x to the third divided by x to the third. What is anything divided by itself equal to? It's always going to be equal to 1. That's why anything raised to the 0 power must equal 1. It really is a cleaned up application of this Law 2 in our exponent rules. So let's look at a few examples, refresh your memory here, make sure we can apply the appropriate law at the appropriate time. The first one, in parentheses, we have 3x squared times y, and the entire thing is raised to the second power. How many different factors do you see in that parentheses? I hope you see 3. We have the constant 3 times x squared times y. All of that's being raised to the second power. So that means we have 3 squared times x squared raised to the second power times y raised to the second power. Now if we clean this up, 3 squared is 9. X squared squared, I have a power raised to a power, so I multiply those exponents, and that gives me x to the fourth, y squared. Okay, so we used a couple of different laws there. We had to use Law 3 when we took everything in the parentheses and rewrote it with each factor being raised to the third power. But then we used Law 5 right here when we saw we had a power raised to another power. Okay, look at number 2. We have a negative 2 squared in a bracket showing the entire expression, negative 2 raised to the second power, is now being raised to the third power. I hope you see we have a power raised to a power. And the base is negative 2. It needs to stay in that parentheses. And then my 2 and my 3 that are exponents get multiplied together and give me a 6. Now, if I'm cleaning this up, I better pay close attention. I have a negative number, but it's raised to an even power. If I have a negative number multiplied together 6 times, that's going to give me a positive, and 2 times 2 times 2 times 2 times 2 times 2 is going to be 64. So that entire thing will simplify to be the number 64. All right, if you look at 3, be very careful with this because not everything has an exponent. In fact, you could think of it this way. You would have 12 divided by negative 4. Just take those constants that are in front, put them together in a fraction and reduce down the way you would normally reduce a fraction, and then apply your exponent rule to the variables that have exponent. I have a to the 7th over a to the 3rd. Now, if I clean up the fraction, 12 divided by negative 4 is obviously negative 3. And now if I use Law 2, which tells me when the bases are the same in a division problem, I subtract exponents, that would give me a to the 7 minus 3 power, which is a to the 4th. Very good. All right, let's look at number 4. This one indicates we need to use the distributive property because we have a term in front of a binomial. So everything in that parentheses must get multiplied by xy squared. If you want, write it out this way. Xy squared gets multiplied by the first term in the parentheses is 3x squared. I have a plus sign. And then xy squared needs to get multiplied by the second term in the parentheses, which is 2y squared. Now, if I clean this up, I'm going to have 3 When I multiply x times x squared, be very careful. What is your exponent on this x? It's a 1. Remember, if I don't see the exponent, I have to remember it's an understood 1. Now, if I'm multiplying x to the first times x squared, make sure you recognize that's x to the third, and then you'd have a y squared with it. That's everything in that first product cleaned up, plus, now if we go to the second product, I have my constant 2, but I only have the x showing up as a factor the one time, so I'm just going to have an x, and if I multiply y squared times y squared, add those exponents and it gives me y to the fourth. Now if we move down to number 5, I hope you're paying attention. What is anything raised to the 0 power? I hope you're going to say 1. It does not matter how many factors are in that parentheses. Whatever it is, the entire thing in parentheses raised to the 0 power has to equal 1. Now when you look at numbers, it actually says number 7 instead of 6 on this page. And what you should notice is, even though I have an exponent that looks a little funny because it's a binomial, it's y plus 2, are my bases the same? They are. So as long as the bases are the same and I'm multiplying, what am I supposed to do with the exponents? Well, I should add them together. So my base remains 4. My exponent will now be the y plus 2, but then I have to add 6 to it. Now, if you get that far, you can probably see this cleans up pretty easily, and it will be 4 raised to the y plus 8 power. We simply combine like terms after we add. And if you look at this last example, we have a to the fourth over b. That fraction is raised to the second power, and then it's multiplied times a squared, b squared, the entire product raised to the third power. So I think we need to remember, we're going to use several laws here. Let's clean it up in parts. If I look at the first fraction, then that's going to become a to the fourth raised to the second, because remember, in a fraction, both the numerator and the denominator get raised to that power. So that a to the fourth raised to the second power means multiply those two exponents, and I'm going to have a to the eighth in the numerator. What will be my denominator? Well, that b has to get raised to the second power, so that will be b squared. Times, now let's clean up the second part of this. We have the product a squared b squared, and that entire thing is raised to the third power. So again, it's that power rule, a power raised to a power. I'm going to have a to the 2 times 3 is a to the 6th. B squared raised to the third power becomes b to the 2 times 3, which is b to the 6th. Now that may look a little funny because our first expression was a fraction. Our second one does not appear to be a fraction, but remember, you can put it over 1. Now we simply need to do a little cleanup. We have 2 rules left to apply here. We have a rule for multiplying and we have a rule for dividing. It doesn't matter which one you use first, but I'm noticing the a's for my bases occur only in the numerator, and those are supposed to be multiplied. So if I multiply a to the 8th times a to the 6th, that gives me a to the 14th. But if I now look at my b terms, I have one in the numerator and one in the denominator. That means I'm going to need to clean up using that quotient rule. If you want, you can write it this way, and that might help you see the cleanup that needs to occur. So if I subtract those exponents, as I am supposed to do, if I'm using the quotient rule, I will end up with a to the 14th, b to the 4th. Now, we're going to use these laws of exponents to solve a few equations here. And as long as you keep in mind that your goal is to try to rewrite each side so that the bases are the same thing, then we will be successful in accomplishing this. And what I'm noticing in number 9 is I have 3 to the x power times 3 to the second power. Now, there are 2 bases that match, And if I'm multiplying and my bases are the same, what should I do with exponents? If you said add them, you got it right. That should be 3 to the x plus 2 power, if I clean up on the left side, is equal to 3 to the 8th power on the right. Now, here's the part you need to be sure you're clear on. If my bases are identical, the only way this equation is true is if my exponents are also identical. That gives me a simple equation I can solve now to find x, because x plus 2 must equal 8 if this is a true equation. If the bases are already equal to each other, the only way the equation is true is if the exponents are also equal to each other. So if I set up x plus 2 equals 8, I can subtract 2 from each side and I would get x equals 6. And I could actually plug that back into the original problem and I could double check to show that the left side will equal the right. Now if you look at 10, very similar, except instead of these exponent expressions being multiplied together, we have the quotient rule we need to use. So if we rewrite this as 3 to the, remember we may have to subtract, it'll be x minus 2 power, is equal to 3 to the 8th power, very much like the last one, except now the exponent on the left is x minus 2, and it has to be set equal to the exponent on the right, which is 8, and in this case, x will equal 10. And again, we could plug it back in to the original problem and see that it really does make the left side equal to the right. If you look at 11, we have a different rule we need to apply here, because we have an expression raised to a power in our numerator. What do you do with those exponents? You multiply them. So that will clean up to be 3 to the 2 times x power over 3 squared, and that would be set equal to 3 to the 8th power. So very much like what we just did on number 10, we are going to have to use that quotient rule, but that means now our exponent on the left side will be 2x minus 2. Remember, with the quotient rule, you subtract your exponents, and that would be equal to 3 to the 8th on the right. Now, if I set 2x minus 2 equal to 8, add 2 to each side, 2x will equal 10, and that means x will equal 5 after I divide each side by 2. One more law of exponent we haven't yet discussed, and that is the law of negative exponents. It is given to you here in Law 7. It says some base raised to a negative exponent is equal to 1 over that base raised to a positive power. Now, very, very carefully make sure you understand this. A negative exponent does not indicate a negative number. Instead, what you want to remember is that a negative exponent identifies location. If you pay attention to what that rule looks like, if I have something with a negative exponent and it would be in the numerator, or if it doesn't look like a fraction, I need to remember it could if I put it over 1, and that would make it in the numerator. It simply tells me take that base to the positive power and take it down to the denominator. If I happen to have a negative exponent in the denominator, it means take that same base, put the positive exponent on it, but take it up to the numerator. Now, I have a variety of ways I can solve expressions that have negative exponents in them, and it sort of depends on what you have, what you may think is the most efficient way to do it. If I look at number 1, I could actually use that law of exponents from before, which tells me if I'm multiplying and the bases are the same, I simply add exponents. Now, if I do that, how much is negative 4 plus 3? Well, that's a negative 1. If I give you the instruction to be sure to write your answer with positive exponents, this is where we need to apply this rule. I wouldn't want to leave it as 5 to the negative 1 power. It means I need to take 5 to the positive 1 power, but take it down to the denominator. If I do that, that will only leave 1 in the numerator, and it would be 5 to the first power. I don't have to put the exponent 1 on there. When the exponent is 1, that's optional. Now, if it's a negative 1, it's not optional. You have to show that there was a negative exponent, but when you clean it up, the 1 is optional. Not required, in fact, preferred not to have it on there. Now, if you look at number 2, we have a negative exponent on a base of 2, and then the entire thing is raised to the second power. So let's use a few rules here. If we have a power raised to a power, we know that means multiply exponents. So that would be 2 to the negative 6th. If I want to rewrite it with a positive exponent, that will become 1 over 2 to the positive 6. That's all you have to do to change a negative exponent to a positive exponent. If I actually wanted to clean this up and simplify it the rest of the way, 2 to the 6th power is the same as 64, and this would be 1 over 64. Now, if we look at these last couple of examples, we have a fraction raised to a negative power. Now, remember, a fraction raised to a power means that I can write the numerator raised to that power over the denominator raised to that power. Okay. What did we say negative exponent tells us? It tells us about location. So we need to move each of these to the other location in order to write it with a positive exponent. That means my 5 to the negative third becomes a 5 to the positive third in the denominator. And because my 4 to the negative third is already in the denominator, I'll bring it to the numerator and write it as 4 to the third power. I now have positive exponents on it, and I can clean this up if I want to simplify the rest of the way. 4 to the third power would be 64, and 5 to the third power would be 125, and that would be my simplified answer. The last example we have, be careful about this one, because remember how I warned you, if you have a constant along with a variable in a parentheses, don't forget the constant gets raised to the exponent as well. So this would equal 2 to the negative 2 power times x to the third raised to the negative 2 power. Now, if we clean this up, that 2 to the negative 2 power will become 1 over 2 to the second times, we're going to have x to the third times negative 2 becomes x to the negative 6, which if I want to get rid of that negative exponent, that's going to mean I have 1 over, now if I clean up 2 to the second power, that becomes 4, and if I change x to the negative 6 so it has a positive exponent, it becomes x to the positive 6 in the denominator. And that would be my simplified answer.